Have you ever frozen at the sight of a spider? That racing heart and surge of adrenaline is your ancient survival mechanism working precisely as evolution intended, the same system that kept your ancestors alive for millions of years. In this video, we'll explore why certain fears seem almost universal, why others are unique to specific cultures, and why that creepy crawly in the corner triggers such an extreme response in so many people. The science behind your fears reveals something fascinating about what makes us human, and why some of our most irrational reactions actually make perfect evolutionary sense. The mystery of universal fears. What if I told you that your deepest fears weren't actually yours, but inherited from ancestors who lived thousands of years ago? Think about it. When was the last time you screamed at the sight of a spider scurrying across your kitchen floor? Now ask yourself, how many people do you know who've actually been harmed by a spider? For most of us, the answer is 0. This fear of 8-legged creatures appears universally across human societies. From the rainforest of Brazil to urban Tokyo, people react with similar discomfort when confronted with spiders, snakes, heights, and the dark. These reactions transcend geography, language, and culture. Here's the strange part. These universal fears don't align with actual modern threats. The lifetime odds of dying from a motor vehicle accident are about 1 in 88, while the odds of dying from a venomous spider are remote, 1 in 483,457. For snakes, it's about 1 in 552,522. You should logically be thousands of times more afraid of your daily commute than any spider in your bathroom. Yet we find our hearts racing at the sight of a harmless house spider while casually texting while driving. This contradiction can't be explained if our fears develop purely from personal experiences or rational assessments of danger. The mystery deepens with identical twins separated at birth. Researchers studying these twins raised in completely different households, sometimes different countries, discovered and often developed the exact same specific phobias despite never sharing an environment. One pair both developed intense fears of water. Another shared an unusual fear of elevators. These weren't common fears taught by parents. They were specific, unusual phobias appearing in both twins independently, suggesting a genetic blueprint for fear responses. Children provide further evidence. A study of suburban American children found they feared mammals and reptiles, snakes, lions, and tigers, rather than the things they were actually taught to be careful about, like street traffic. The Child Fund Alliance discovered that across both developing and developed countries, the most common fear among children worldwide is dangerous animals and insects. These patterns suggest our fear responses come pre-installed, like factory default settings that can be modified but never fully erased. The timing of fear development is equally telling. The most basic fears, sudden, loud noises, and rapidly approaching objects appear in infants with no prior learning. A baby who has never experienced danger will still startle and cry at a loud bang or something rushing toward their face. We share these responses with many other species as hardwired features of our nervous systems. This brings us to the central question. If these fears aren't based on personal experience or actual environmental dangers, where do they come from? Why do they follow such specific patterns across different cultures and in people who share genetic material but not environments? The answer lies in our evolutionary past. Those fears you experience, the racing heart, the surge of adrenaline, the instinctive recoil, are echoes from your ancestors. They're responses that kept humans alive for millions of years, passed down through generations in your DNA. Our earliest human ancestors, who quickly feared and avoided snakes, spiders, heights, and the dark, were more likely to survive than those who approached these potential threats with curiosity. A fear of snakes prevented deadly bites. A fear of heights prevented fatal falls. A fear of the dark kept them safe from predators hunting at night. Over countless generations, these survival-enhancing fear responses became encoded in our genes. The humans who survived to reproduce were often those who had these protective fears, passing those tendencies to their children. When we jump at the sight of a spider, we're experiencing an ancient survival mechanism preserved through natural selection. This explains why certain fears appear universal while others vary between cultures. The genetically hardwired fears, loud noises, falling, snakes, spiders, show remarkable consistency across different societies. A study comparing Chinese and British female students found fears with early biological relevance, such as darkness and heights, showed no cultural differences. Both groups rank these fears similarly despite their different upbringings. However, socially learned fears show cultural variations. These fears develop through learning and cultural transmission rather than genetic inheritance. Social fears and fears of specific situations often differ between cultures because they're learned from our environment. This genetic predisposition doesn't mean we're destined to have phobias. Rather, we have what scientists call prepared fears, innate tendencies requiring environmental input for activation. Your fear system allows for environmental calibration, adapting to threats specific to your local environment. Your genetic predisposition might make it easier to develop a fear of snakes, but you might not develop that fear if you grow up handling snakes safely. What's fascinating is how this system works neurologically. Your brain contains specialized circuits that detect and respond to certain threats before conscious awareness. This happens in a primitive part of your brain that evolved before human consciousness. When you jump at something snake-like in your peripheral vision, your body responds before your conscious mind processes what you're seeing. This system was brilliant for ancestral threats, but isn't designed for modern dangers. Your brain's fear circuits don't activate as effectively for climate change, financial insecurity, or radiation dangers without clear sensory triggers that our ancestors never encountered. That's why we often fear the wrong things. Our ancient brain runs outdated software. Understanding the evolutionary roots of our fears gives us power over them. It explains why certain phobias are so common and difficult to overcome through logic. Your fear of spiders isn't irrational. It's ancestral wisdom encoded in your genes. This ancient fear response system is what we'll explore next, the specific brain structures that detect danger and trigger that cascade of physical reactions before you're even aware of what's happening. Your brain's ancient alarm system. Have you ever jumped at a sudden noise before you even realized what it was? That strange moment when your body reacts before your mind catches up isn't a glitch. It's your brain's prehistoric security system at work. This reaction happens because your brain contains an ancient alarm system that's been keeping your ancestors alive for millions of years. At the center of this alarm system sits the amygdala, a tiny almond-shaped structure buried deep in your brain. Despite its small size, about the volume of a small grape, the amygdala wields enormous power over your emotional responses, especially fear. Think of the amygdala as your brain's security guard, constantly scanning for danger and ready to hit the panic button at the first sign of threat. When you see something potentially dangerous, like a dark shape on a forest path, your brain processes this information along two separate routes simultaneously. The first route is the high road, where visual information travels from your eyes to your visual cortex for detailed processing. This pathway is thorough, allowing you to consciously recognize what you're seeing. The second is a low road, a neural shortcut that sends rough, unprocessed information directly to your amygdala, bypassing conscious thought entirely. Imagine your brain as a large office building. Most information follows the proper channels, coming through reception, getting processed by various departments, and finally reaching the executive suite, your conscious mind, for decision-making. But the amygdala operates like an emergency fire alarm system that can trigger a building evacuation without waiting for the executive's approval. Sometimes this alarm goes off when there's no actual fire, like when a toaster burns some bread, yet everyone must react as if there's genuine danger. The system evolved because waiting for conscious recognition of a predator could mean the difference between life and death. The amygdala's direct information channel creates a peculiar experience. Your body begins responding to danger before you're even aware of what you've seen. Your heart races, muscles tense, and adrenaline surges through your bloodstream, all before you consciously register the snake-like shape on the path, which might just be a twisted stick. This rapid response occurs through an efficient chain reaction. Once the amygdala detects a potential threat, it signals the hypothalamus, another small structure near the base of your brain. The hypothalamus functions as your body's command center, controlling automatic functions like body temperature, hunger, and the release of stress hormones. When the hypothalamus receives the alarm signal, it activates two systems. First, it triggers the sympathetic nervous system, your body's emergency response network. This system sends signals to organs throughout your body, preparing you for immediate action. Your heart beats faster, breathing quickens, pupils dilate, and blood vessels in your digestive system constrict to divert blood to your muscles and brain. Simultaneously, the hypothalamus activates your adrenal glands, which release adrenaline and other stress hormones into your bloodstream. Within seconds, these hormones reach cells throughout your body, amplifying the effects of the nervous system activation. This entire sequence constitutes the fight or flight response. Your body prepares for either confronting the danger or escaping from it. The biological machinery behind this response is virtually identical to what your ancient ancestors experienced when facing a predator. For our ancestors, this system was perfectly adapted to their environment. When a rustle in the grass might signal a lurking predator, the ability to respond instantly could save your life. Over countless generations, natural selection refined this system into the hair-trigger alarm we all carry today. Research has revealed the remarkable speed of this system. Your amygdala can detect a threat and initiate a fear response in as little as 50 milliseconds, just 1/20th of a second. For comparison, it takes about 300 to 500 milliseconds for visual information to reach your conscious awareness. This speed differential means your body begins responding to danger a full quarter second before you're even aware of what you've seen. But what are the practical implications of this timing mismatch? In one fascinating study, participants were shown images of fearful faces so quickly that the subjects couldn't consciously see them. Despite reporting no awareness of the images, their amygdala is activated, showing that this brain structure processes emotional information below the threshold of consciousness. This system still works the same way today as it did for our ancestors, even though our environment has dramatically changed. When you jump in a horror movie jump scare, your amygdala triggers the same cascade of responses that would help you escape a predator. The preservation of this system across mammalian species suggests its critical survival value. Rats, rabbits, monkeys, and humans all share similar fear circuitry. The fear circuit is so fundamental that damage to the amygdala can eliminate the ability to recognize danger. Patients with amygdala damage might casually pick up venomous snakes without any fear response. When your amygdala receives that rough signal suggesting danger, it immediately activates, sending signals to over a dozen different brain regions simultaneously. Some signals control heart rate, breathing, and sweating. Others direct your attention to the potential threat. More go to areas handling memory formation, which is why emotionally charged events are remembered so vividly. All this happens before your visual cortex finishes processing what you're seeing. By the time your conscious mind can say, that's just a garden hose, not a snake, your body is already in full fight or flight mode. This explains why you feel foolish after being startled. Your conscious mind is catching up to a response already underway. The most remarkable aspect is that this system operates entirely outside your control. You can't decide not to flinch when something rapidly approaches your face. These are automatic responses generated by neural circuits that evolved before human consciousness. This ancient alarm system responds differently to various potential threats. In our next section, we'll explore evolution's most wanted list, the specific threats our brains are hardwired to detect and avoid. Evolution's most wanted list. Why do so many people scream at the sight of a tiny spider when they calmly drive cars daily, despite cars being infinitely more dangerous? This contrast reveals something fascinating about how our brains process threats. In the United States alone, motor vehicle accidents claim over 38,000 lives annually, while spider bites cause about 7 deaths per decade. Statistically speaking, your car is roughly 5,000 times more likely to kill you than any spider. Yet most people feel perfectly comfortable behind the wheel, while experiencing intense fear at the sight of a harmless house spider. This discrepancy points to what scientists call prepared fears, specific fears that humans seem biologically predisposed to develop. These fears connect directly to the neural circuitry we discussed earlier, representing tendencies our brains have evolved to acquire quickly when exposed to certain triggers. Your brain essentially has special receptors for certain types of dangers, receptors that are particularly sensitive and ready to form strong connections. The evolutionary puzzle here is striking. Why would our brains develop special sensitivity to threats that pose minimal danger in modern environments? The answer requires thinking about the world our ancestors inhabited, not the world we live in today. 4. Millions of years, our primate ancestors lived in environments where venomous creatures like snakes and spiders ranked high on the threat list. Imagine an early human ancestor foraging in dense vegetation. Suddenly they spot a distinctive pattern among the leaves, the scale pattern of a venomous snake. Their heart races, muscles tense, and they leap backward. This split-second reaction saves their life, while their companion, who reacted more slowly, suffers a fatal bite. This scenario played out countless times over millions of years, gradually shaping our neural architecture. Consider the evolutionary timeline. Primates have shared their habitats with venomous snakes for approximately 40 to 60 million years, while modern humans have only existed for about 300,000 years. In environments without medical treatment, a single bite from a venomous creature meant certain death. Individuals with neural circuits that quickly identify these threats would survive and reproduce, shaping our brain's threat detection system over generations. Research across species and age groups supports this theory. Lab-raised monkeys who have never encountered snakes still display fear responses when first shown snake images, a response built into their neural circuitry. Similarly, 6-month-old babies shown images of snakes and spiders alongside flowers and frogs consistently look longer at the dangerous animals and show signs of distress, despite having no previous exposure to them. This suggests our brains programmed to pay special attention to certain ancient dangers before we develop language or conscious understanding of threats. The specialized detection system affects how quickly we learn to fear specific stimuli. When researchers paired images of flowers, mushrooms, spiders, and snakes with identical mild electric shocks, participants developed much stronger fear responses to the spider and snake images than to the flower and mushroom images. Our brains more readily form fear associations with evolutionary relevant threats. Natural selection favored these quick fear responses because in survival situations, false positives were less costly than false negatives. Mistaking a curved stick for a snake costs only a moment of unnecessary fear, while mistaking a snake for a stick costs your life. This better safe than sorry principle explains why our fear system tends to be hypersensitive to certain triggers, even when irrational in modern contexts. These prepared fears extend beyond snakes and spiders. Humans also seem predisposed to quickly develop fears of heights, enclosed spaces, deep water, blood, and darkness. Fear of heights protected ancestors from deadly falls. Fear of enclosed spaces kept them from situations where predators could trap them. Fear of deep water prevented drowning among those who couldn't swim. Fear of blood signaled serious injury. Fear of darkness warned of nocturnal predators. Even certain social fears protected us by maintaining vital group connections when isolation meant vulnerability. Research confirms these fears are remarkably consistent across diverse cultures, from industrialized nations to hunter-gatherer societies. Studies of identical twins separated at birth provide compelling evidence of the genetic component of these fears. Despite growing up in completely different environments, sometimes in different countries, identical twins often develop the same specific phobias, like twins who both developed intense fears of water or elevators despite no contact with each other. These genetic predispositions don't do much to eternal fear. Many people overcome these fears through exposure and learning. However, our brains are set up to more easily develop certain fears than others, as if evolution has highlighted specific threats in our mental landscape. This evolutionary perspective explains why developing a spider phobia is easier than fearing electrical outlets, despite the latter being far more dangerous in modern homes. Our ancient brain wasn't designed to perceive abstract or modern threats with the same emotional intensity as threats that plagued our ancestors for millions of years. This mismatch between our evolved fear responses and modern dangers creates significant challenges. While we easily fear spiders and snakes, we struggle to generate appropriate fear responses to genuinely dangerous modern threats like climate change, radiation, or cars. Our brains aren't evolutionarily prepared to recognize these dangers, which lack the immediate sensory characteristics that trigger our ancient alarm system. This evolutionary mismatch between our ancient brains and modern threats is what we'll explore next. Modern threats versus ancient wiring. What happens when our Stone Age brains try to process nuclear radiation, climate change, or artificial intelligence? These dangers are very real, possibly even more threatening than the predators our ancestors faced, yet many of us struggle to feel the appropriate level of fear when confronted with them. This creates a dangerous mismatch between what actually threatens us and what our brains are prepared to fear. Our fear system evolved to deal with immediate, concrete threats, things you could see, hear, smell, or touch. Venomous animals with distinctive shapes, approaching predators with growling sounds, heights with clear visual cues. The system works brilliantly for these dangers, triggering rapid responses that could save your life. But this same system falters when confronted with modern threats that lack these sensory characteristics. Modern dangers fundamentally clash with our ancient neural wiring because they operate outside our sensory detection systems. Think about radiation exposure. Despite being potentially lethal, radiation has no smell, no taste, no sound, and is completely invisible to the human eye. Our ancestors never encountered radiation as a distinct threat, so we never evolved the neural circuitry to detect or fear it. The same applies to carbon monoxide, electrical current, and many toxic chemicals, all invisible killers that our senses can't detect. This sensory invisibility creates a significant problem for our fear system. Without clear sensory input, the amygdala, our brain's threat detector, doesn't automatically activate. There's no low-road shortcut to trigger an immediate fear response. Instead, we're forced to rely on abstract understanding and conscious risk assessment, processes that are much slower, require education, and are easily overwhelmed by more immediate concerns. These modern threats resemble invisible software bugs in upgraded technology. While our brains are remarkable hardware optimized for Stone Age survival, we now face software-level threats our systems weren't designed to detect. Just as a computer might continue running while malware silently compromises the security, our brains often fail to sound alarms about dangers that lack sensory signatures. This explains why people often fear the wrong things. Take aviation versus driving. Flying triggers significant anxiety for many people, with about 40% of the general population reporting some fear of flying. Yet commercial air travel is remarkably safe. Your odds of dying in a plane crash are about 1 in 11 million. Meanwhile, car accidents kill over 1.3 million people worldwide each year, making them roughly 500 times more dangerous than planes. Despite this stark difference in actual risk, many people who fear flying think nothing of texting while driving. The pattern repeats with other modern versus ancient threats. People fear shark attacks, which kill about 5 people worldwide annually, more than heart disease, which kills about 18 million. They worry more about terrorist attacks than falling in their own bathrooms, despite the latter being far more likely to harm. These misaligned fears follow a predictable pattern based on certain characteristics. Research shows that we tend to fear threats that are unfamiliar, catastrophic in potential impact, outside our control, and caused by human action rather than nature. This explains why nuclear power plants generate more fear than cigarettes, despite tobacco causing vastly more deaths. Nuclear accidents are unfamiliar, potentially catastrophic, outside individual control, and human-made, hitting all the fear triggers. Smoking feels familiar, produces harm gradually, seems within personal control, and involves a natural substance. Modern threats like electricity, chemicals, and radiation trigger different emotional responses than ancestral threats. A fascinating study found that while ancestral threats like snakes and spiders typically trigger a mixture of fear and disgust, modern threats often generate different emotional combinations. Researchers discovered that the strongest fear response is triggered by modern threats like electricity and car accidents, while the highest levels of disgust are evoked by ancient threats such as body waste products and worms. This suggests our emotional system is more flexible than we might assume. We can learn to fear modern dangers, but the emotional quality differs from our responses to evolutionary threats. With modern threats, fear often mixes with anger, particularly when resulting from human actions. Without clear sensory input, climate change, electromagnetic radiation, or microplastics in bloodstream remain abstract concepts rather than visceral dangers. We understand them intellectually but struggle to feel them emotionally. This explains why many people acknowledge climate change as real but don't feel the urgent fear that might motivate immediate action. Research shows we often respond with anger rather than fear to modern environmental threats like pollution. This anger response may reflect a sense of moral violation, that someone has deliberately created danger for others rather than the pure survival fear triggered by predators. This emotional difference matters because fear and anger motivate different behaviors. Fear typically triggers avoidance and protective measures. Anger often motivates confrontation and punitive actions. Can our brains adapt to properly fear what actually threatens us today? The evidence suggests both yes and no. Our brains are remarkably plastic, capable of forming new associations throughout life. We can learn to fear modern threats through education and experience, yet these learned fears rarely have the same visceral, automatic quality as our evolutionary prepared fears. They require conscious attention and often fade when we're distracted by more immediate concerns. When properly understood, modern threats can trigger stronger fear responses than ancestral dangers. Education and proper risk communication are essential for helping our Stone Age brains navigate modern dangers. We need to translate abstract threats into forms our ancient fear system can process, making the invisible visible, the gradual immediate, and the abstract concrete. Our evolutionary prepared fears represent only part of our emotional responses to threats. Culture plays an enormous role in determining which dangers we fear and how we express those fears. While our biological tendencies create certain universal patterns, cultural factors can amplify some fears while diminishing others. Some fears exist only within specific cultural contexts, created through shared beliefs rather than biological programming. These cultural fear fingerprints remind us that human fear is always a complex interaction. Did you know there's a phobia in Japan that doesn't exist in America, and fears in Mexico that would baffle Europeans? While we all share those basic biological fears we just discussed, spiders, snakes, heights, cultures around the world have developed their own unique fear fingerprints that often make absolutely no sense outside their original context. These cultural fear patterns go far beyond our evolutionary programming. They're learned, shared, and reinforced through generations, creating phobias that can be powerful enough to disrupt daily life, yet exist only within specific cultural boundaries. Each society develops its own catalog of acceptable things to fear, a cultural fear menu that members unconsciously select from. Consider South Korea's widespread belief in fan death, the conviction that sleeping in a closed room with an electric fan running can lead to hypothermia and death. Korean fans typically come with timers to automatically shut off during the night. To most Americans or Europeans, this fear seems completely irrational, yet in South Korea it remains a genuine concern. In Japan, taijin kaifusho affects many individuals. Unlike Western social anxiety, which focuses on embarrassing oneself, this disorder centers on the fear of offending others through inappropriate social behavior. This disorder highlights the importance of face and reputation in Japanese culture, where social harmony is highly valued. Meanwhile, in Southeast Asia, tetraphobia, the fear of the number 4, influences everything from building design to daily activities because of the phonetic similarity between 4 and death in many Asian languages. In other parts of Southeast Asia, a condition called koro involves the fear that one's genitals are retracting into the body, potentially causing death. Despite making no medical sense, it has caused mass hysteria events affecting thousands simultaneously. What creates these cultural fear fingerprints? Think of our biology as a canvas upon which culture paints unique patterns. The base canvas contains our evolutionary fears, but culture applies distinct brushstrokes that create a finished portrait unique to each society. These cultural anxieties emerge through social learning, media influence, folklore, and collective reinforcement. Social learning transmits cultural fears when children observe their parents' reactions to specific situations and adopt similar responses. Media amplifies these patterns through news reports and entertainment that target culturally relevant fears. Cultural narratives and folklore serve as powerful vehicles for transmitting fears, embedding moral lessons alongside fear conditioning. Research reveals fascinating differences between collectivist and individualist societies. A comparative study found that collectivistic countries tend to be more accepting of socially reticent behaviors, while individualistic countries are more accepting of expressions of individuality. In collectivistic cultures, there are more rules and guidelines for social behavior, making social missteps more obvious than in individualistic cultures. This pattern appears across regions. Sweden exhibits unusually high rates of social phobia, with above 15% of the adult population affected. Some researchers connect this to Sweden's cultural emphasis on social isolation. While it is a bit harder to find exact numbers on children, surveys show that it is an even bigger problem in children, suggesting that at least some grow out of it. Economic factors create unique cultural fears as well. In the United States, significant anxiety surrounds ambulance services costs, rooted in the American healthcare system, where many individuals lack adequate insurance coverage. This anxiety makes little sense in countries with universal healthcare systems, yet it profoundly shapes behavior in the American context. Many cultural fears serve adaptive functions within their societies. The Japanese fear of offending others helps maintain social harmony in a densely populated society where cooperation is essential. Mexico's cultural reluctance to say no stems from a cultural emphasis on politeness, friendliness, and prioritizing family and community, helping preserve social bonds even at the cost of directness. Environmental factors shape cultural fears too. In India, the fear of stray dogs is common, stemming from the prevalence of stray dogs and the frequency of dog attacks. This fear makes perfect sense given the local conditions and public health challenges. A compelling study comparing Chinese and British female students found that while they generally ranked fearful objects similarly, their fear intensities differed significantly. Most importantly, the fears that showed no cultural differences were those that had early biological relevance, such as fear of the dark and of high places. Only the socially learned fears show cultural differences. This confirms that our evolutionary fears create a common foundation, but culture builds distinct structures on top of this shared biological base. These cultural fear fingerprints reveal the complex interplay between our biology and social environment. We're the result of both forces interacting in complex ways. Our brains come pre-wired with certain fear tendencies, but culture shapes how these tendencies express themselves and adds entirely new fears to our emotional repertoire. As we continue to explore the psychology of fear, we need to understand how these fear responses develop throughout childhood. Our fears don't appear all at once. They emerge in predictable patterns that match specific developmental stages. This timeline of fear shows us how our brains gradually calibrate their threat detection systems as we grow from infants to adults. Growing up scared, the timeline of fear. Why do babies fear strangers but not heights, while toddlers fear monsters but not traffic? The fears children experience aren't random. They follow a remarkable pattern that unfolds like clockwork across different cultures. This timeline of fear reveals something fascinating about our brains. Specific fears emerge at predictable ages, regardless of where a child grows up or what their parents teach them. Have you ever noticed how a 4-month-old baby will happily go to anyone, while that same baby at 8 months might burst into tears when a stranger approaches? This transformation happens almost overnight, like a switch flipping from trust to caution. Around 7 to 9 months, babies develop stranger anxiety, a wariness of unfamiliar faces that coincides with two crucial developments, understanding that people exist when out of sight, object permanence, and beginning to crawl. This pattern appears universally. Studies of infants across rural Africa, urban Japan, and suburban America show stranger anxiety emerging at the same developmental window, suggesting an evolutionary purpose rather than random emotional development. The evolutionary logic becomes clear when considering our ancestral environment. When infants began crawling, their vulnerability shifted dramatically. Before mobility, babies stay where caregivers place them. Once crawling, they could potentially move towards strangers who might pose threats. Developing stranger anxiety precisely when mobility begins served as a protective mechanism. During this same period, 10 to 18 months, separation anxiety emerges to stress when caregivers leave. This fear develops as infants realize parents continue to exist when out of sight, but they lack understanding that parents will reliably return. For our ancestors, separation from caregivers could be life-threatening. Infants who cried when separated would draw caregivers back, increasing survival chances. Early mobility phase, 6 to 12 months. Despite developing anxiety about strangers and separation, most infants show no fear of heights, dangerous animals, or darkness. A crawling 9-month-old will happily approach ledges unless prevented. Studies using visual cliffs, glass surfaces creating the illusion of a drop-off, demonstrate that most crawling babies will venture right over what appears to be a dangerous edge. Walking phase, 12 to 18 months, the fear of heights typically develops only after several weeks of walking experience. Once toddlers begin walking upright, falls become more hazardous. Height anxiety emerges precisely when this protection becomes necessary. This fear correlates with walking experience rather than age, suggesting it's tied specifically to this new mobility mode. Imagination phase, ages 2 to 6. As children reach ages 2 to 3, new developmental milestones bring new fears. 1. Imagination-based fears ages 2 to 3. With developing abstract thinking comes fear of monsters, ghosts, and darkness. These fears typically peak around ages 4 to 6, when children can vividly imagine threats but struggle to distinguish fantasy from reality. Number 2. Animal fears. Ages 4 to 6. Children commonly develop specific fears of predators like lions, tigers, and bears, often animals they've never encountered directly. Research shows suburban American children fear these animals more than daily dangers like traffic or household hazards. What's remarkable is how these fears follow the same developmental pattern across cultures, despite different folklore and predator species. International studies confirm that dangerous animals and insects rank among the most common childhood fears worldwide, rather than the actual threats specific to children's environments. Each fear emerges when it would have offered maximum protection in our ancestral environment. Children become afraid of predators around ages 4 to 6 precisely when, throughout human evolution, they would have begun exploring further from adult protection. The predictable sequence suggests our fear responses develop gradually as we acquire motor and cognitive skills that historically exposed us to specific dangers. Rather than being born with fully formed fear systems, children receive a developmental curriculum of fears, each appearing when it will provide maximum protection while allowing necessary exploration. This evolutionary calendar explains why childhood fears often seem irrational today. A child terrified of monsters but casually running into traffic isn't making poor risk assessments. They're following an ancient developmental program calibrated for environments very different from our modern world. What causes these specific fears at such predictable ages? Evidence suggests evolution has programmed our brains to develop fears in lockstep with capabilities that would have exposed us to specific dangers. As Boyer and Bergstrom note, these fears emerge when children are most vulnerable to the dangers targeted by the fears, or more precisely, when children would have been most vulnerable to such dangers in ancestral environments. This timeline represents how our evolutionary past shapes emotional development. Our fear system unfolds gradually, activating specific fear modules precisely when they would have been most beneficial throughout our species' history. While our modern environment differs dramatically from the one in which these fear responses evolved, understanding this developmental pattern helps explain many seemingly irrational childhood fears. It also reveals how our emotional systems are calibrated for specific threats that pose the greatest risk at particular developmental stages. This developmental pattern shows our brain processing potential threats through different systems at different ages. But there's another fascinating aspect to how our brains respond to danger, the way we process disease threats differently from predator threats through our disgust defense system. The disgust defense system. What if I told you that your feeling of disgust when seeing rotting food is actually a sophisticated disease avoidance system millions of years in the making? That instinctive revulsion you feel when you smell something putrid or see a cockroach scuttle across your kitchen floor isn't just an emotional reaction. It's an ancient biological defense mechanism that protected your ancestors long before anyone knew germs existed. While fear protects us from immediate physical dangers like predators or falling, disgust serves as a parallel protective system with a very different purpose, keeping us safe from invisible threats like bacteria, viruses, and parasites. This behavioral immune system evolved as a first line of defense against disease, operating through a completely separate emotional and physical pathway than our fear responses. What makes this system particularly fascinating is how it creates such different physical reactions than fear. When you're afraid, your body prepares for action, your heart races, adrenaline surges, and you're ready to fight or flee. But disgust triggers almost the opposite response. Your heart rate may actually slow down. You might feel nauseous or want to vomit. Your facial expression changes in a specific way. Narrowed nostrils, raised upper lip, wrinkled nose, a universal expression recognized across cultures. These physical reactions serve a specific purpose: to reject potentially contaminated substances and distance yourself from sources of infection. Think about what happens when you smell spoiled food. That immediate nausea and urge to turn away physically removes you from something that could make you sick. The facial expression of disgust, constricting your nose and mouth, literally reduces how much you might inhale or ingest of whatever dangerous substance you've encountered. Even the nausea and potential vomiting serve a protective function, helping you expel anything potentially harmful that you might have consumed. This physical response is hardwired into our neural architecture. Your brain processes disgust primarily through the anterior insular cortex and basal ganglia, with additional regions working together as part of a specialized network. This architecture functions much like a sophisticated quality control system in food production, constantly monitoring sensory input, automatically flagging potential contaminants, and triggering immediate rejection protocols when necessary. This disgust defense system appears remarkably consistent across cultures. Studies show that certain disgust triggers are virtually universal: bodily waste like feces, urine, vomit, and blood, visible signs of disease or poor hygiene in others, spoiled or unfamiliar food, and certain animals associated with decay, disease, or parasites. Whether you're studying people in New York, New Delhi, or rural Papua New Guinea, these core disgust elicitors remain remarkably similar. This universality makes perfect sense from an evolutionary perspective. Throughout human history, feces have been consistent sources of harmful pathogens. Bodily fluids like blood could transmit disease. Spoiled food contained dangerous bacteria. Our ancestors who avoided these disease vectors through disgust responses were more likely to survive and pass on their genes, including their disgust reactions. Research with non-human primates supports this evolutionary view. Studies found that mandrills tend to avoid highly parasitized fecal samples, suggesting that disgust as a disease avoidance mechanism emerged early in primate evolution. This ancient origin explains why disgust reactions feel so automatic and visceral. They're the product of millions of years of evolutionary pressure. The disgust system likely started with a simple response to bad taste, which often indicates spoiled food. Over time, this system expanded to include visual and olfactory cues that might signal contamination, creating a more sophisticated defense against disease. Eventually, disgust triggers expanded to include social and moral violations, what we might call moral disgust at behaviors like cheating or cruelty. What's particularly interesting is how disgust sensitivity varies between individuals. Some people have highly sensitive disgust responses, reacting strongly to potential contaminants, while others show much milder reactions to the same stimuli. This variation correlates with various personality traits and even political orientations, suggesting that disgust sensitivity shapes how we view the world far beyond simple pathogen avoidance. While the disgust system evolved to protect us from natural disease threats, it sometimes struggles with modern threats that don't fit its ancient programming. Invisible modern dangers like toxic chemicals and radioactivity don't trigger disgust, despite being harmful contaminants. Research shows these modern threats actually elicit strong fear responses instead. This makes sense when we consider that disgust evolved specifically to deal with organic contaminants with specific sensory properties. The sophistication of this disgust defense system becomes even more apparent when we recognize how it must balance protection against overreaction. Being too disgusted by everything would prevent beneficial activities like trying new foods or interacting with others. Being insufficiently disgusted would leave us vulnerable to disease. Natural selection has calibrated this system to follow a better safe than sorry approach, slightly overreacting to potential contamination because historically, the cost of getting sick far outweighed the cost of unnecessary avoidance. Understanding this behavioral immune system helps explain many otherwise puzzling human behaviors, why we're reluctant to share drinking glasses, why we find certain animals inherently repulsive despite their harmlessness, and why we might avoid perfectly safe food that simply looks unusual. Think about your visceral reaction when spotting a greasy smudge on a restaurant glass or noticing flies buzzing around a buffet. That automatic recoil is your ancient defense system working exactly as designed. While fear and disgust both serve protective functions, they represent different evolutionary solutions to different types of threats. This distinction helps explain why we sometimes find ourselves strangely attracted to fear-inducing stimuli, the thrill of horror movies or roller coasters, while almost never seeking out experiences that trigger disgust. This peculiar attraction to fear, rather than disgust, reveals another fascinating aspect of our emotional architecture that we'll explore next: the thrill of fear. Why do we pay good money to watch horror movies that trigger the exact same fear responses our brains evolved to avoid? It seems completely irrational when you think about it. Our ancestors who survived were the ones who ran from danger, not the ones who willingly sought it out. Yet millions of us line up to watch masked killers chase teenagers to abandoned buildings or demons possess innocent families. We ride roller coasters that make our hearts race and our palms sweat. We visit haunted houses where strangers in costumes jump out at us from dark corners. This creates a fascinating paradox for scientists who study emotion. Why would activities that trigger our ancient fear system, the very emotions we're biologically programmed to avoid, become sources of entertainment and even pleasure? The answer lies in a complex interaction between our biology, psychology, and the special context we create for these experiences. The key to understanding recreational fear is the concept of safety. When you watch a horror movie, your conscious brain knows you're safe in a theater or on your couch, even as your ancient fear circuits respond to the threatening images on screen. This creates a unique psychological state that researchers call bounded fear, fear experienced within clear boundaries that signal safety. Your body produces the physiological arousal associated with fear, but your higher cognitive functions interpret this arousal differently because of the context. This safety context allows you to experience the physical sensations of fear, racing heart, heightened awareness, adrenaline rush without the negative emotional aspects that would normally accompany genuine danger. You get the exciting physiological activation without the actual threat, similar to how a roller coaster provides a sensation of falling without the danger of hitting the ground. During these experiences, fear triggers a powerful cocktail of chemicals. Adrenaline increases your heart rate, dopamine floods your brain creating pleasure, and endorphins release creating euphoria. This neurochemical combination creates a powerful experience many find highly pleasurable. This physiological arousal enhances other emotional experiences, including attraction. Picture this scenario. Male participants in a study conducted by psychologist Arthur Aaron crossed either a high, swaying, unstable bridge, inducing fear, or a low, stable bridge. Midway across, they met a female research assistant who gave them her phone number after administering a survey. The results? Men who crossed the scary bridge were significantly more likely to call the assistant afterward than those who crossed a stable bridge. Why? The researchers discovered the men misattributed some of their physiological arousal from fear to attraction toward the woman. Their racing hearts and heightened awareness, triggered by the scary bridge, intensified their perception of attraction. This phenomenon, called excitation transfer, shows how arousal from fear can spill over and amplify other emotional states, including sexual attraction. This connection between fear and attraction might explain why horror movies often include romantic subplots, or why scary movies make popular date choices. The physical arousal from fear may enhance feelings of attraction between viewers, suggesting an evolutionary advantage to enjoying fear in certain contexts. Individuals experiencing controlled fear might form stronger social bonds through shared emotional experiences. Horror filmmakers target our evolutionary prepared fears to create maximum impact. The most effective movie monsters exploit specific fears that would have threatened our ancestors. Researchers have identified several categories of ancestral threats that appear repeatedly in horror fiction: predation, being hunted, violence from other humans, contamination and disease, social exclusion, and dangerous environmental features. Examine the most successful horror villains, and you'll see these ancient fears at work. Predatory monsters like the alien in Alien trigger our fear of being hunted. Slasher villains like Michael Myers embody human violence. Zombies represent contamination and disease. Ghosts often reflect fears of social isolation. Each taps into a different category of threat that evolution prepared us to fear. The timing and nature of scares in horror films mimic real-world threats. Jump scares trigger our startle reflex, an automatic response that protected our ancestors from sudden ambush predators. Extended tension scenes exploit our response to stalking predators. Even the musical cues in horror films often mimic sounds that would signal danger in nature. Does this attraction to recreational fear serve any evolutionary purpose? Some scientists suggest that controlled fear experiences might function as a form of emotional practice. By voluntarily exposing ourselves to fear in safe contexts, we might be rehearsing how to handle real threats. This emotional training could potentially improve our ability to regulate fear responses in genuine danger situations. Others propose that thrill-seeking might be tied to individual differences in how our brains process dopamine. People with certain genetic variations affecting dopamine receptors may require more intense stimulation to feel the same level of reward. The connection between fear and attraction reveals another possible evolutionary advantage. Shared thrilling experiences might strengthen social and romantic bonds. When people experience intense emotions together, they often feel more connected afterward. This emotional contagion could potentially strengthen group cohesion, valuable for our ancestors' survival. Our attraction to recreational fear tells us something important about human psychology. We don't simply seek pleasure and avoid pain. Rather, we seek meaning, novelty, and emotional intensity, even if that intensity includes emotions that feel unpleasant in other contexts. Fear, when experienced safely, offers a unique combination of physiological arousal and cognitive engagement that many find deeply satisfying. This understanding of recreational fear has practical applications beyond entertainment. The same principles that make horror movies frightening, yet enjoyable, are now being applied in new, therapeutic approaches for treating actual phobias. Rewiring
Something we'll
fear.
explore in our
Modern
next
treatments.
on cutting-edge treatments
What
for
if you could
phobias.
cure a lifelong phobia without ever consciously seeing what you fear? Imagine overcoming your terror of spiders without ever looking at a single spider. This isn't science fiction. It's the cutting edge of modern phobia treatment, where neuroscientists are rewiring fear circuits by understanding exactly how they work in the brain. For decades, the gold standard treatment for phobias has been exposure therapy, gradually facing your fears in a safe environment until they lose their power. This approach works because of how our brains process fear. When you repeatedly encounter a feared stimulus without anything bad happening, your brain forms new neural pathways that override the fear association. Traditional exposure therapy involves creating a fear hierarchy, a ladder of increasingly frightening encounters with your phobia trigger. If you're afraid of spiders, you might start with cartoon spiders, then photographs, then a spider in a sealed container, and eventually allow a spider to crawl on your hand. Each step is repeated until your anxiety decreases before moving to the next level. This approach is remarkably effective. Research shows exposure therapy works well for specific phobias, whether delivered over multiple sessions or in a single intensive treatment. A meta-analysis found that condensed treatment can be just as effective as longer programs. Some people who suffer from severe phobias for decades find themselves largely cured after just a few hours of properly conducted exposure therapy. The effectiveness of exposure therapy makes sense when we examine brain activity. The amygdala, that almond-shaped threat detector mentioned earlier, gets retrained during exposure. Essentially, you're teaching it that the stimulus doesn't predict danger. Your brain forms inhibitory connections that suppress the fear response. However, exposure therapy has a significant drawback. It requires experiencing fear during treatment. For people with severe phobias, even looking at pictures of their feared object can trigger panic attacks and overwhelming anxiety. This makes some patients reluctant to seek treatment, while others drop out before completing therapy. Cognitive behavioral therapy, CBT, helps address this by combining exposure with techniques to manage anxiety. Patients learn to challenge irrational thoughts and develop coping strategies like breathing exercises. CBT breaks the avoidance cycle by addressing both physical and mental aspects of phobias. But what if we could bypass conscious fear entirely while still retraining the brain? This is where recent breakthroughs in unconscious exposure therapy come in. Remember those two separate pathways for processing threats? A high road through the conscious brain and a low road directly to the amygdala? Unconscious exposure therapy targets that low road without engaging the high road, exposing your amygdala to the feared stimulus without your conscious mind recognizing what you've seen. Take Sarah, who couldn't even look at spider images without panic attacks. Her therapist used very brief exposure, flashing spider images for milliseconds before masking them with benign pictures. Throughout entire sessions, Sarah never consciously saw spiders or felt afraid, yet her brain was learning that spiders didn't predict danger. Another innovative approach called spiderless arachnophobia therapy shows people objects resembling spiders without triggering conscious recognition. Patients might view a camera tripod with bent legs that subtly mirrors a spider's shape. While patients don't consciously register these as spider-like, their brain's unconscious processing system gradually associates these features with safety rather than danger. These unconscious approaches work because our brains process threats through separate unconscious and conscious pathways. When someone with a spider phobia is repeatedly exposed to spider images they can't consciously perceive, their amygdala detects the potential threat, but without triggering the racing heart or feeling of fear. This recalibrates the amygdala without suffering. Technology is expanding treatment possibilities further. Virtual reality exposure therapy, VRET, creates controlled encounters with feared situations through immersive simulations. This is particularly valuable for phobias difficult to recreate in therapy offices, fear of flying heights, or public speaking. Studies show VRET significantly reduces distress and avoidance behaviors after just 6 30-minute sessions, with benefits persisting during follow-up. Virtual reality offers precise control. Therapists can adjust threat levels, increasing difficulty as patient comfort grows. They can instantly pause or modify experiences if anxiety becomes overwhelming, creating a safe space to practice facing fears without real-world unpredictability. These advances stem from the two-system approach to understanding fear. Recognizing different neural circuits handle different aspects of fear response. By targeting specific circuits, treatments can be tailored to individual patients and their unique fear processing patterns. The evidence suggests these neuroscience-based approaches work for both universal biological fears and culturally specific phobias. While phobia content may vary across cultures, the underlying fear circuits function similarly in all human brains. Exposure therapy, both conscious and unconscious, has shown effectiveness across different cultural contexts. The most remarkable aspect of these treatments is what they reveal about fear itself. Overcoming phobias without consciously facing them demonstrates how much emotional processing happens below awareness. Your conscious experience of fear is just one part of a complex system evolved for protection. This understanding gives us new power over our emotional responses. By working with our brain's natural learning mechanisms, we can reshape deeply ingrained fears. Our fears may be ancient, but our ability to understand and modify them represents an impressive achievement of modern neuroscience. As we conclude our exploration of fear, let's examine how these ancient systems interact with modern threats by exploring a fascinating case study, how our brains process pandemic fears. Pandemic fears, a case study. What makes pandemic fears different from other fears you experience? Think about it. A pandemic activates both our ancient brain systems and our modern thinking simultaneously, creating a unique emotional cocktail unlike any other threat we face. Pandemics offer a fascinating window into how our brains process danger. They sit at the intersection of ancient biological threats our ancestors faced and abstract modern hazards our Stone Age brains weren't designed to handle. When a pandemic strikes, it triggers a complex mixture of fear, disgust, and moral outrage all at once, an emotional storm that rattles both our primitive and rational systems. Picture what happened during the early days of COVID-19. You likely experienced the traditional fear response, racing heart, heightened alertness, anxiety about the future. But alongside that fear, you probably felt disgust when thinking about the virus itself and how it spreads. Many people reported feeling physically repulsed by the thought of contaminated surfaces or being close to potentially infected individuals. This disgust response comes straight from our behavioral immune system, that ancient disease avoidance mechanism we discussed earlier. These emotional systems evolved to handle very different types of threats. Fear typically responds to immediate dangers with clear sensory signals, predators, heights, loud noises. Disgust responds to contamination and disease risk with visible cues like decay or unusual appearance. But viruses challenge both systems because they're invisible to our senses. This invisibility creates a significant problem for our brain's threat detection system. Without clear sensory input, our ancient alarm system, the amygdala and its connected circuits, doesn't automatically activate. There's no low-road shortcut to trigger an immediate response. Instead, we're forced to rely on abstract understanding and conscious risk assessment, processes that are much slower and more easily influenced by other factors. This is why pandemic fears often seem either exaggerated or inadequate compared to the actual risk. Without direct sensory evidence of danger, our emotional responses depend heavily on information from other sources, media reports, government announcements, social media, and the visible behavior of those around us. Our brains essentially outsource threat detection to these external sources rather than making direct assessments. The COVID-19 pandemic revealed fascinating cultural differences in how people respond to collective threats. Some societies emphasize collective responsibility and adherence to protective measures, while others place greater emphasis on individual freedoms and personal risk assessment. These different responses reflected deep cultural values about the relationship between individuals and their communities. Many East Asian societies with stronger collectivist traditions showed higher compliance with mask wearing and social distancing measures early in the pandemic. Meanwhile, some Western countries with stronger individualist traditions experienced more resistance to these same measures. This pattern reveals how our cultural programming shapes our response to threats that affect entire communities. Media coverage played a crucial role in shaping pandemic fear responses, often amplifying anxiety beyond what direct experience might suggest. The constant stream of information created what researchers call an infodemic alongside the pandemic itself. Studies found that heavy consumption of pandemic-related news correlated with increased anxiety and stress-related disorders, even among people who hadn't personally experienced COVID-19. This influence of information on our fear experience is uniquely human. While other animals learn to fear specific threats through direct experience or observation, only humans can develop fear responses based on abstract information communicated through language and media. This capacity allows us to prepare for dangers we haven't personally encountered, but it also makes us vulnerable to fear responses that don't match actual threats in our environment. What distinguishes pandemic fears is how they trigger multiple emotional systems simultaneously. The COVID-19 pandemic engendered uncertainty and fear due to its rapid spread and high mortality rates. But alongside this fear, people experienced disgust toward behaviors perceived as risky and moral outrage toward those who didn't comply with protective measures. This moral dimension sets pandemic fears apart from other threats. When someone doesn't wear a mask during a pandemic, they're potentially endangering others. This adds a layer of anger and moral judgment to our emotional response that isn't present when facing a spider or standing at a great height. The pandemic functioned as both a health threat and a moral situation that engaged our social emotions. The COVID-19 pandemic also created multiple psychosocial stressors. Economic instability, job loss, financial strains, creating fertile ground for increased anger. This mixture of health fears, economic anxiety, social isolation, and uncertainty created a complex emotional landscape, unlike anything most people had previously experienced. These pandemic responses reveal something fascinating about how humans handle threats. We integrate multiple overlapping systems, from ancient disgust responses to sophisticated moral reasoning, creating a uniquely human experience of threat. This integration allows us extraordinary flexibility in responding to new dangers, but it also creates vulnerability to misalignment between our different response systems. Our ancient disgust system might push us toward avoidance, while our rational risk assessment suggests a different approach. These conflicting signals can create internal confusion and social conflict during threats that affect entire communities. Pandemic fears highlight how our ancient brain systems interact with modern cultural programming. The basic mechanisms of fear and disgust appear across all human cultures, but how these emotions express themselves varies significantly based on cultural context. Our biology provides the emotional palette, but culture determines how we paint with those colors. This perspective on pandemic fears brings us to a broader understanding of human fear in general. Our fears represent a complex integration of ancient biological wisdom with modern cultural learning, a blend that makes human emotional life uniquely rich and complex. As we conclude our exploration of fear, we can see that the roots of our fears reach deep into our evolutionary past while extending into our cultural present. The next time you feel afraid, remember that you're experiencing a sophisticated emotional system designed by millions of years of natural selection and shaped by thousands of years of cultural evolution. Our fears tell a fascinating story about who we are, creatures with ancient brains navigating a modern world. Every time you feel that surge of adrenaline, you're experiencing the voice of evolution speaking through you, trying to keep you safe in ways that made sense for millions of years. Understanding these ancient roots gives us power over our emotional responses. We can recognize which fears serve us today and which are simply echoes of a world long gone. What fears might you be carrying that no longer serve you? By examining our reactions through this evolutionary lens, we gain not just knowledge, but the freedom to choose how we respond to the world around us.